Our team has conducted a series of scaled prototype tests to validate the flight capabilities, redundancy, and scalability of our design. What follows are highlights that demonstrate the extent of our prototype's performance, and why these results give confidence in the success of our full-scale system. We began with controlled hover testing using safety tethers. Hovering is the most power-demanding flight regime, and demonstrating stable lift and control here provides strong validation of our design's vertical flight capability. The use of tethers allowed us to test safely while confirming that our control system responds reliably under high-thrust conditions. Here you can see that the vehicle remains stable and controllable in hover, even with external disturbance forces like the safety tethers pulling on it when they stretch out. Next, we performed a critical redundancy test by intentionally shutting down and removing two engines. Here, you can see the front and rear engines have been removed, along with their support beam structure. Even under this severe condition, the drone remained fully controllable and was able to complete the minimum mission profile, covering 30 meters and then going back. This demonstrates the robustness of our design and provides direct evidence that the full-scale aircraft will maintain safe, stable flight even in the event of multiple propulsion failures, a vital requirement for air ambulance missions. The 20% scaled model was built several months before the 35% prototype as an early validation vehicle, focused purely on testing the hexacopter configuration stability and controllability. By flying this smaller model first, our team was able to reduce risk from the larger build, ensuring there would be no unexpected behaviors when the 35% prototype took flight. Both vehicles use the AirDoPilot control environment, which meant lessons learned on the 5th scale aircraft directly streamlined setup and tuning of the larger 35% scale prototype. This stepwise approach reflects aerospace best practices for reducing technical risk and proving airworthiness.
Touchdown.
To demonstrate consistency across scales, we flew our 35% prototype alongside a 20% early validation model. Despite their different sizes, both aircraft performed the same maneuvers with similar stability and control responses. This parallel testing confirms that our configuration scales reliably, strengthening confidence that the full-scale aircraft will be able to achieve the same flight profiles, controllability, and stability. In this video, you can see the 35% scale and the 20% scale prototypes flying side by side, able to complete the same flight profile with similar responses. Again, demonstrating scalability and proving that the 100% scale would behave similarly as well. Together, these demonstrations validate that our design is ready to scale. The stability proven in hover and maneuvering, the resilience under two engines inoperative, and the repeatable performance across both the 20% and 35% prototypes collectively show that the full-scale vehicle will competently complete the required mission profiles. In the productivity mission, the system can be quickly deployed and make repeated payload trips with efficiency and reliability. In the adversity mission, the demonstrated control authority and redundancy confirm that the aircraft will safely take off, land, and operate even in sandy, sloped, wet, windy, or unsurveyed sites. And in the maneuvering mission, the proven agility and precision at scale indicate that the vehicle will be able to slalom tightly around obstacles and perform spot landings, both with and without payload. These results provide strong evidence that our full-scale air ambulance will complete these missions with confidence, safety, and ease, ensuring reliable performance when it matters most.